Hi there! Continuing the talks on special usage for power supply circuits, today we will introduce the concept of voltage multiplier, a device that is capable of taking a voltage in input and creating in output one of a higher value. Before getting into the details, please take a moment to subscribe to this channel and consider becoming a patron to help make new and better videos for you to enjoy. Information is available in the description below. Let's now see what exactly is a voltage multiplier and how it works. There are two main categories of voltage multipliers. They both produce a voltage higher than the one that is available, but one kind creates it out of another smaller DC voltage, while the other creates it out of an AC voltage. We call them DCDC voltage multipliers and AC-DC voltage multipliers. Let's examine, step by step, how an ideal DC-DC voltage multiplier works. Here is the concept diagram. The battery on the left powers the circuit, and the switch S1 moves continuously between the positive of the battery and ground. The common terminal of the switch is connected to the left lead of capacitor C1. Then we have diodes D1 and D2 in series. Their central connection is also connected to the other lead of capacitor C1. A second capacitor C2 is connected in parallel to the series of diodes. The output is taken at the positive lead of C2. To make easy to understand what happens when we power up this circuit, I decided to run a simulation and obtain from it the diagrams of the voltage transients in the key points and at the output. Here is the circuit that I used for that. To be able to run the simulation, I had to find a way to automate the switch S1 while keeping a constant voltage on the upper end of D1 and C2. I did that by replacing the battery and the switch with a couple of generators. The first generator, a constant voltage generator, provides the fixed voltage that we need. The second generator replaces the battery and the switch S1, providing a square wave going into the left lead of C1. In addition to that, I directed the simulator to continuously probe the voltage in three key points: the output of the square wave generator, the middle point between the diodes, and the output of the circuit, to generate the diagrams of the transient that happen in the first 2 seconds after the circuit is powered up. The signal that drives the whole circuit is of course the square wave. Let's see what happens each time its voltage changes. When we power up the circuit, the square wave value is 0 volts, which basically connects C1 to ground. In this condition, diode D1 is forward biased, with a positive on the anode and ground on the cathode through C1, and therefore can conduce current. We say that the diode is on. Since D1 is on, the constant voltage generator can charge C1, which will reach the voltage of Vin, which for this simulation is set to 5 volts. At this time, C2 is isolated because it has the same voltage at both of its ends, since both D1 and D2 are on. As a result, Vout is the same as Vin, or 5 volts. Next, the square wave changes to 5 volts, and at the point in between the D1 and D2, the voltage, which is the sum of the one of the generator and the one of C1, spikes up. This turns off D1, since now the voltage of the cathode is higher than the one at the anode. D2 instead will remain on, and a current will flow from the generator and C1 into C2 across D2. As a result, half of the charge of C1 will transfer to C2. The change of the charge will cause the voltage on C1 to drop to about 7.58 volts, and the voltage on C2 and the output will increase to about the same value, actually a little less because of the drop in voltage across D2. Now the square wave changes again and returns to 0 volts. This time, both C1 and C2 are charged and have already a certain voltage at their leads. Because the left end of C1 is now connected to ground and the right side is connected to the constant generator, its voltage will go back to Vin, minus the drop caused by D1. In the meantime, D2 is now off, because the voltage at the anode is less than the voltage at the cathode, which is the voltage of C2, and therefore there will be no current going in or out of C2, and its voltage will not change, as well as the output voltage. But when the square wave goes back to Vin or 5 volts, D1 will go off, and D2 will go on. As a result, more charges will leave C1 and will transfer to C2, which will increase a little bit more its voltage. And since the voltage on C2 has increased, so has Vout. And this process will continue until after a number of cycles C2 will be fully charged at the same voltage as the constant generator. This process will continue until after a number of cycles C2 will be fully charged at the same voltage as the constant generator. At that point, the output voltage will be increased to twice the voltage of the constant generator, as you can see now in the full diagram. And so, this circuit is in effect a voltage multiplier by 2. Let's see now how we can practically build a circuit that works like that. The core of this circuit is once again a 555 timer, which I used to generate the square wave that I needed. Resistor R1 and R2, along with capacitor C2, are calculated to provide a square wave with a duty cycle of about 0.5 with a frequency of about 3.8 kHz plus minus 400 Hz, according to the tolerances of the components, especially C2. Capacitor C5 is used to keep stable the voltage provided by the power supply, which I fixed to 12 volts. Capacitor C3 is required by the IC specs to keep stable the reference voltage generated inside the 555. The output is on pin 3, which goes directly toward C4, which along with C1, D1 and D2 is part of the circuitry to double the variable 12 volts. This circuit is supposed to provide at its output a voltage of 2 times 12 volts DC or 24 volts DC, without considering the voltage drops on the diodes and with no load. In fact, since this is a practical circuit, we should be able to use the output voltage on a load. However, as we will see in lab in a few moments, draining current from this circuit will cause the output capacitor to discharge on the load, which will cause the output voltage to drop. The higher the current on the load, the higher will be the voltage drop. And this is something similar to what we saw a few weeks ago in my video on polarity inverters. And here is the circuit assembled on a breadboard. Here is the AC555 that acts as a square wave generator. Of these 3 capacitors, the first is the one that is used to filter the power supply, and these 2 capacitors are those that, with the help of these 2 diodes, double the variable voltage. If I powered this circuit with a 5 volts power supply, I would obtain 10 volts on the output. If I powered the circuit with a 12 volts power supply, I would obtain an output of 24 volts, and so on. The limit here is just given by the minimum and maximum voltage that the 555 can tolerate. This capacitor on the right is the one that basically filters the reference voltage on pin 5 of the IC. The other one is the 100 nanofarad capacitor that, along with these 2 resistors, provide the timing for the 555. The signal, like we said already, will be a square wave with a duty cycle of about 0.5 or 50%. And the frequency should be around 3.7 kHz, besides the tolerances of the components, of course. I also added 3 pin headers. I will use this one to connect the instruments to the ground of the circuit. This other one is the actual output, and the last one, connected to pin 3 of the 555, is the one that will allow us to check that the signal is an actual square wave at 3.7 kHz. The power supply is connected through this cable to my DC power supply, which is currently providing 12 volts. You can also see the current absorbed by the circuit, which is about 3 mA. This is in fact what is needed to keep the output voltage at the max value of 24 volts, while some energy is dissipated by the parasitic resistances of the circuit components and by the breadboard itself. In addition, I also connected the probe of the oscilloscope to the pin 3 of the 555, which will allow us to see the square wave piloting the voltage multiplier. And here is the image on the oscilloscope, where we can also see the frequency of this square wave, which is about 3.8 kHz, very close to the calculated value. Note also the amplitude of the wave, which, considering that the oscilloscope is set to 5 volts per division, give us the amplitude of the signal on about 12 volts, which is what we expected actually. the exact voltage can be measured with the multimeter functionality of the oscilloscope, and you see that in reality it seems to be just above what we expected. But this is within the tolerances of the voltmeter of the power supply, which has not the same precision as the oscilloscope. Now, you might think that I could use an actual digital multimeter to measure the values. However, the multimeter will not show me the peak value that I want, but only the RMS value, which in this case will be around 6 volts. I'm now going to change the position of the oscilloscope probe so I can measure the actual output voltage of the circuit. I will also have to adjust the sensitivity of the oscilloscope since now the voltage is too high to be seen on the screen. And here, now that I lowered the sensitivity to 10 volts per division, we can see again the signal, which is now a DC voltage of about 23.2 volts, as we expected. Note also that this time I am making the reading on the main value, that is because the output voltage is not exactly constant. In reality, there is a little ripple that we cannot see with this sensitivity, but that the oscilloscope can still measure. And it is this one, the peak-to-peak value, which is around 1.2 volts. At this point, I would like to show you what happens if we attach a load to the output of this circuit. As we said earlier, we can anticipate that the load will cause the voltage to drop. But now let's see in practice if this will happen and how much. To do this experiment, I used the electronic load I presented some time ago on this channel. Note that just by attaching the load, even if it is at its minimum, the output voltage has already dropped significantly. And this can be seen both on the voltmeter of the electronic load and on the oscilloscope. I will now start increasing the current on the load, and we can measure on the ammeter on the power supply how much we are using, while the voltmeter of the load and the oscilloscope will tell us how much is the corresponding drop of voltage. See, the voltage has dropped significantly just with a load of about 40 mA. Let's now take a look at this other schematic of voltage multiplier. It is basically the same concept as the previous one, but this time we have two equal stages in series of each other, this one on top and this other one on the bottom. Each stage is absolutely identical to the previous, but now we use the output of the first stage as the source of constant voltage of the second stage. In the first stage, the output voltage was given by the sum of the voltage of the power supply plus the voltage of the capacitor C2, which was the same as the power supply, thus providing us with twice the voltage of the power supply. In the second stage, the output voltage will be given by the sum of the voltage of the power supply plus the voltage of the capacitor C3, which is the same as the output of the first stage, thus giving us 3 times the value of the power supply. Looking at the diagrams on the right side, we can see that things work similarly as in the previous schematic. The main difference is that now we will be charging more capacitors, and as a result it will take more cycles to complete the transient and reach the final voltage. Let's take a quick look more closely. The first diagram shows the signal coming from the square wave generator. This is identical to the one in the previous circuit. The second diagram shows the voltage of the connection between the diodes in the first stage. Again, this diagram looks like the same as the previous circuit. The third diagram represents the voltage at the output of the first stage. This one too is similar to the one of the previous circuit. However, you can see that now, since we are applying a load to its output, the voltage takes more time to stabilize. Not much though. In fact, after a couple of seconds, we can still reach a voltage that is double the one of the power supply. The fourth diagram comes from the connection between the two diodes on the second stage. If you compare it with the diagram obtained from the same point of the first stage, you'll see that they are quite similar. This time, however, because we are powering this second stage with the output of the first stage, the voltage goes up to a higher value, and in doing so, it spends a little more time for the upper side of the wave to reach the final voltage. And finally, the last diagram represents the output at the second stage. This one too is similar to the one at the output of the first stage, which is the third diagram. However, the final voltage in this diagram is 3 times the voltage of the power supply. Let's now rearrange the components of this diagram in a slightly different way that will help us to see something more. I have removed the generators and went back to the switch to make the schematic simpler, so we can concentrate on the multiplication stages. The working principle still stands, of course. If you take a close look, the multiplication stages are exactly the same as before. I just rotated a picture of each stage and I drew the diodes in a way that makes it easier to see what I need to show you. Now, each stage has a shape of a triangle, and we already learned that each triangle increases the output voltage by an amount equal to the voltage of the power supply. So, directly at the power supply we have a voltage V. At the end of the first stage we have a voltage 2 times V. At the end of the second stage we have a voltage of 3 times V. Do you see the pattern? Every time I add a new stage, the voltage increases 1 times more of the previous. So we can actually put as many stages as we want, one after another, and at the end, the output voltage will increase to a number given by the voltage of the power supply multiplied by the number of stages plus 1. So, for example, if we add a total of 9 stages, we will have an output of 10 times the voltage of the power supply. Cool, isn't it? If you look closely to this picture, you will notice that the output voltage is actually the sum of the power supply voltage plus the voltage of each capacitor in series with the power supply. Each one of these capacitors is charged so that it will have a voltage equal to the power supply, but all these capacitors are in series, and so the voltage keeps adding up at the output. And the nicest thing of all is that even if we were building a circuit with a lot of stages, producing a very high voltage, each capacitor does not need to work at that high voltage, but just at the voltage of the power supply. So at the end, this is a low-cost way to obtain high voltages, given that we do not try to extract a lot of current. Otherwise, like we have seen in lab with the first circuit, the output voltage will start dropping. To demonstrate that we can really keep increasing the voltage adding multiple stages, I built this second circuit that provides 3 times the power supply voltage. I'm not going to describe how this circuit works, since now it should be obvious. Just note that now there are 2 stages here on the right. And notice also that now we have C1 and C6 in series, which, along with the power supply, will provide an output voltage of 3 times the power supply. Let's prove that in lab. Here is the new circuit, which I assembled again on a breadboard. This side is exactly the same as the previous circuit and provides the square wave to make the rest of the circuit function. These capacitors and diodes make up the first stage of this voltage multiplier, and this is the new stage with its 2 capacitors and 2 diodes. And it is exactly the same as the first stage. Again, there is a header from where we can extract the square wave, and another one at the output of the second stage. If I power the circuit with 12 volts, like I did with the previous one, we should now see an output voltage of about 36 volts, which is 3 times 12. Let's now connect the power. The workbench power supply still provides 12 volts, and you can see that the circuit is absorbing at 2 mA, about the same as the previous one. And now let's connect the oscilloscope probe to the ground and to the output of the 555. On the oscilloscope we can now see a square wave. This time the frequency is higher than before. Well, I used the same component values, but because of the tolerances that's what we got. The peak-to-peak voltage is 13 volts, and since this is a square wave with a 0.5 duty cycle, the medium wave is about half of the 13 volts. And here I read 6.2 volts. Let's now take a look at the output of this circuit by moving the oscilloscope probe on this other header. And of course, since the voltage is higher, the oscilloscope is out of scale and we cannot see anything on the monitor. Oh well. Changing the scale on the oscilloscope, we can see again the signal, which looks like it has a value of 34 volts, with a ripple of about 1.2 volts. But because of the scale, on the monitor we can just see the straight line of the mean value. The 34 volts are reasonable considering the voltage drops on all the diodes and the ripple. And now I will connect the electronic load, so we can verify that absorbing current from this circuit will lower the value of the output voltage. With a load at a minimum, the voltage is now 31.9 volts, and making a higher current flow, the voltage will start to drop. At about 40 milliamps, the voltage drops in fact to around 28 volts. Note on the oscilloscope that once we start drawing current from the electronic load, the ripple will increase, and if I increase the current, the ripple becomes greater and greater. And that is the actual reason why we read a lower average voltage of the output of the circuit. The last thing I want to show you in this video is how to do a similar voltage multiplier without using a square wave oscillator. The trick is to use a power supply that has a voltage that oscillates on its own, basically an AC voltage, like the one we have from the AC power from the main line, which however provides a sine wave rather than a square wave. The circuit works similarly to the ones we saw previously. This time, however, we don't need the square wave generator, because the power supply is already an alternate current, like the one you can get from a power outlet or from a transformer. Capacitor C1 is put in series with the generator, and the diode D1 connects the other end of the capacitor to ground. With this kind of connection, every time the generator output is negative with respect to ground, the capacitor will be charged through D1. When the generator provides a positive voltage with respect to ground, the output on the cathode of D1 will become the sum of the voltage of the generator plus the voltage of the capacitor. And since the generator provides an alternate current and the capacitor is charged to a fixed voltage, we end up with a sum that is like a sine wave shifted toward the positive, like in this second diagram. If we now add another capacitor and another diode like this, we can extract at the end of the second capacitor a voltage that is almost constant, like you can see in this last diagram. And that is because the second diode operates like a rectifier and charges the capacitor C2 every time there is a positive crest in the sine wave. Note, however, how there is a small but still visible ripple superimposed to the DC voltage of the output. And, like we did with the DCDC multiplier, we can keep adding stages to this AC DC multiplier to obtain higher and higher voltages. Here is what happens adding one more pair of diode and capacitor. This new stage is powered by the voltage present at the output of C1, which is still a sine wave but shifted toward the positive. Because the input of this last stage is a sine wave, it will work like the very first stage and will produce a voltage like the one in diagram 4. Basically, we have created another sine wave even more shifted toward the positive. And now, if we add one more diode and capacitor, we can rectify again the last signal and obtain an almost constant voltage at the end of this last capacitor, like in this diagram on the bottom right of the picture. Like we did with the DCDC multiplier, we can draw the circuit in a slightly different way to better recognize the various stages. This is a circuit with one stage, with 2 stages, with 3 stages, 4 stages, and so forth. It is just a bunch of components organized in triangles. The more the triangles, the more the stages. We can extract the output at any node where a capacitor is attached to. However, all the nodes on the top of the picture will present a sine wave shifted toward the positive, and all the nodes on the bottom of the picture will present a rectified voltage and therefore a more constant voltage. You can use any node as the output, and every time you move to the next node from left to right, the voltage will keep increasing accordingly. However, if you need a constant output voltage, only the bottom nodes are good, as the ones on the top still have a strong ripple equal to the actual amplitude of the generator in the left. The schematic of a real AC-DC voltage multiplier is essentially the same as the theoretical one. This is the one that is capable of providing twice the voltage of the generator. The only difference with the theoretical schematic is that we will use now a real sine wave generator. I will show you this circuit in the lab in a moment, and I will use a function generator set to provide a frequency of 4 kHz. However, it is also possible to use the same frequency of the voltage from the power outlet, 50 or 60 Hz depending on where you live. And here is the schematic for a multiplier by 3. And a multiplier by 4. I just need to keep adding new stages until I reach the multiplier that I need. For the lab, I just built a circuit with 4 stages, and I can show you the output for each one of them one by one. In this picture you can clearly see the diodes and the capacitors of each cell. At the first cell we'll have the same voltage as the generator, but shifted up. At the second cell we'll have twice as much, at the third cell it will be 3 times, and so forth. And here is the function generator I will use to power the circuit. I will set the frequency to 4 kHz and the voltage to 12 volts. Let's now connect the cable to the input of the circuit, ground connector and signal connector. I will also use the oscilloscope to show you the output signals. Here is the ground connection of the oscilloscope, and this is the probe at the output of the generator. Let's look at the input signal through the oscilloscope. The single peak of the sine wave with respect to ground is only half of the full peak-to-peak voltage of the sine wave. In this case I am reading a peak-to-peak voltage of 13.2 volts, but the single peak is at 6.6 volts. And this is the voltage that will charge the capacitor of the first stage of the circuit, not the peak-to-peak one. The first stage of the multiplier will shift the sine wave by 6.6 volts, giving us an all-positive sine wave. We can see this by connecting the oscilloscope at the output of the first stage. Here you see that the original sine wave has now been shifted up. The peak-to-peak value is still the same, but now we have increased the top value of the sine wave from 6.6 volts to 12.4, which is the original 13.2 minus the drop of the first diode. However, the average of this signal is still around 6 volts, and this proves that stage 1 provides only a multiplication by 1. I will also add that this, being an odd-numbered stage, provides at its output still a sine wave, but shifted up, so the signal is always positive. Let's move the oscilloscope probe to the output of the second stage now. This is the stage that will rectify and increase the signal at the first stage. As you can see, now we have a real DC voltage, and its value is double the average value of stage 1, or 11.4 volts. Stage 2 multiplies the original positive side of the sine wave by 2 and makes it a real DC voltage. Let's now look at the output of stage 3. You see, now the sine wave has shifted more toward the positive, and its average value is now 16.8 volts, or 3 times the value of the positive side of the original sine wave, considering of course the voltage drop on the diodes. And finally, let's look at the fourth stage. And of course, well, now we are out of the scale. Here, now we can see it. As expected, at the fourth stage we have a nice DC voltage, and its value is 22.4 volts, which is the original 6 volts times the stage number, which is 4, minus the voltage drop on the diodes of course. Let's now add a load to the output to see the effect of the load on the output voltage. Ground goes here, and the actual load is connected to the output of stage 4. The electronic load is set to its minimum, but already this way we can see a noticeable effect on the output. The voltage has dropped considerably, and there is a very visible ripple on top of the DC signal. If now we increase the load, the voltage drops considerably, and this can be seen both on the oscilloscope and on the voltmeter of the electronic load. This tells us that this kind of circuit allows to considerably increase the voltage, but this voltage can just be used as a sort of static source, or in other words, they can be used whenever we need a high voltage, but with a negligible available power. So why do we care? Well, think of those devices like the taser guns, or those devices that use electrostatic fields to remove dust particles from the air. Both of them, and many others, use high voltages, but they don't need any current, or maybe just a very modest amount of it, and that is where these voltage multipliers excel. However, when we need high voltages with high powers, we need to go back to more traditional ways, like the usage of transformers. In fact, to transfer the same amount of power with a transformer at high voltages, we end up spending less than building a multiplicator circuit. And also, at the end, transformers end up being even smaller than such multipliers. For example, nobody would use a voltage multiplier to obtain the 1000 volts needed to make a microwave oven work, considering that the need power is significantly high, in the order of the hundreds of watts. A transformer works much better in this case, and that's what is used in the microwave ovens. And now, a big thanks to you for following this video up to the end. Please let me know through the comments if you found this tutorial useful and if you would like to see more of them. And once again, if you liked this video and the channel, please subscribe and consider becoming a patron. Links for donations are in the description below. I'll see you in the next video, and in the meantime, happy experiments!